I'm going to experiment with this view because I have never done that before. Oh, that is not good. All right, yeah, we'll just we'll work with that. All right, so what are the objectives and learning outcomes here? So the idea is that we are going to, by the end of this, you should be able to understand what Dasymetric modeling is, understand what random forests are and their constituent parts, and apply these concepts to population modeling, so that hopefully you can then carry out a Dasymetric population model and then critically assess the limits and strengths of such a model. And then hopefully, fingers crossed, and I'm sure you all will, you all seem rather bright, is be able to further study and iterate and expand on this method with your own data, or make your own flavors of it, really, because this is really a framework as opposed to a prescribed singular method, as I alluded to with the PopRF expansion, for any sort of model to generate weights. So what is the general problem? The general problem is that we typically get census data that is in polygons, and that just gives you a count, right? A population count over an area. And lacking any other information, we have to kind of make the naive assumption that, okay, population is homogeneously spread throughout this through each individual polygon. If you think of something like a county, that's a rather large administrative area, right? And we know that people don't live everywhere. You're not going to have a lot of people living in the middle of lakes, or in the sea if there's a coastal area that's included in that polygon. You're not going to have folks living in industrial estates likely, and each census or each polygonal population data set has its own sort of resolution, right? So this one's rather fine in the city here that we're looking at. It's very well defined. It looks like it might even be at block or multiple block level. That's pretty good, right? And if you look at the global context, this is excellent because sometimes we only get things at like admin level 3, so that's not, or admin level 2, so that's not like the national level, which is 0. The first level, which is like state or provinces, and 2, which is about like counties or the secondary administrative division. That's not usually the case. And even with this, we don't know about the heterogeneity of where population is within this area. So the idea is, how do we go from something like this, which is relatively coarse, relative, to something like this, which is much finer? And so this here is a raster data set on the bottom as opposed to vector, where each pixel in this case represents 25 by 25 meters on the ground. So relatively fine. So how do we go from something that we have very little information about, we can only make naive assumptions, to something that is much more fine resolution and hopefully informed and more realistic of where population is likely to be? So this is where Dasymetric weighting comes in. But before we get to that, we're going to look at something called aerial reweighting, which is related but quite similar. And this is a figure from the PopRF vignette, which is included in the GitHub repo, but also there's a DOI in it where I've got it hosted on my ResearchGate. So essentially with aerial reweighting, you have this idea of source areas and target areas, and source areas being your original coarser units, and target areas being the finer units within the source areas that you want your data to be disaggregated at, right? And disaggregation just being taking your values from a larger area and reassigning them to the smaller areas in some informed way. In aerial reweighting, it assumes that you are redistributing stuff based upon the proportional area. So if I start with these two source areas on the left, A and B, that have 10 people in it and 20 people in it respectively, and I want to transfer it to 3 target areas, so we've got A, AB, and B, we can look at what proportion of the original source areas is in relation to the new areas, the target areas. So in this case, half of AB is made up of 1/3 of A, and I will highlight that. So this is sort of the new area here. 1/3 of the AB area is, well, half of the new AB area is 1/3 of the original B, and then our new A and our new B are 2/3 of their original. So areal reweighting is quite simple in the sense that we just then take those proportions and multiply them by their original count value, right? So in that case, the new A becomes 2/3 times 10. The new B becomes 2/3 times 20. And the new center area is 1/3 of both A and B put together. This comes out to either some decimal or fractional thing that I won't work out. But the main thing is that all of these values add back up to the sum of original values. So if you were to add all these up here on the right, they add back up to a sum of 30, which is the total of A and B. And not only that, if we were to take half of this new center one, which has a value of 10, and were to add it in the new A area here on the left, these would add back up to the original A area of 10. And similar with B, it would add back up to 20. Now, this is a key property of not only areal reweighting, but dasymetric reweighting. It's called volume preserving or pycnophylactic, which I might be able to remember how to spell. Pycnophylactic. And this was originally a term stated by Waldo Tobler in the 97 paper. So Tobler did a lot of dasymetric modeling later on, including the first gridded population of the world dataset, GPW, produced by Season out of University of Columbia in conjunction with NASA. But this is one of the main benefits of dasymetric reweighting, is that no matter how you disaggregate it, it can always be added back up. The target areas and their values can always be added back up to their original value, right? So no matter what, we're not destroying information here if we go back to the original source level and source units. Is that clear for everyone? That makes sense? I'm seeing nodding heads. All right, cool. So let's make it a little more complicated of, okay, well, what if we areas, everything's not homogeneously distributed and we can't assume that population is, that we can take proportional area. And this is where we come into dasymetric disaggregation. And there's many different flavors of dasymetric disaggregation, but I'll cover sort of the main ones. So dasymetric disaggregation is essentially saying, okay, we've got a source area and a value, or source areas and values, and corresponding target areas that are within them. So this figure, which is also from the vignette, we're going to look at just one area, but it can be generalized to multiple areas as well. It's the same procedure, just applied. So essentially the idea is, how do we get from source areas to target areas? Again, if we're not doing it by proportional area, how do we come up with weights for this? Now, one flavor of dasymetric disaggregation is, okay, well, we will manually assign the weights a priori based upon expert knowledge of some sort. So a common data set or information that's used to assign weights is land cover. So, the idea that, okay, if we look at built settlement areas with built land cover, we can expect relatively higher population counts and population densities compared to agricultural land cover versus forested land cover versus swamp land cover, etc. So you can assign these weights, and using an expert knowledge, you might just get some folks in a room who decide, okay, well, I'm going to assign a weight of 0.15 to settlement areas, a weight of 0.1 to rural areas, well, agricultural land cover, a weight of 0 to water bodies, so on and so forth, to where each land cover that you have has a weight, and all those weights add up to 1, right? That's a key point with weights. So the problem with this is that, it's not the most empirical thing. It's not saying that it's not useful, but it's not necessarily data driven, although there can be benefits to this that are less quantifiable. So knowledge of local histories and trajectories of population distributions in relation to other things. Sometimes these things do have a positive impact on how something performs. Another type of Dasymetric disaggregation, which is the one we're going to focus on here, is called Intelligent Dasymetric Disaggregation. And I don't think you can see me while sharing screen, but I'm putting air quotes around intelligent. It gives it more credit than it should. It's essentially you're using some sort of statistical model to determine weights, whether that's a linear regression and getting weights from coefficients, or a machine learning method like random forest to determine the weights, etc. You're using some sort of observed data and so ancillary data being informative data that's other than population. In this case, an example, land cover, and you have population count data of some sort. Now, there's two main ways you can train this model, right? If you have some areas that are target areas that you've got population counts for, great. You can train the model on the same level that you're going to predict at. So, say this is a 100-meter resolution, then we have our population counts at, and we'll just use a linear regression here for a simple example. Our population counts are some linear combination of weights based upon the observed relationships between the covariates, right? However, oftentimes finding population data that's at such a fine resolution as you might be wanting to predict at means that you don't actually have that. So another thing you can do, which is kind of unconventional, but in practice has worked quite well, is you can actually take your coarser source units. So say you've got counties, or in this case, you've just got, you've got multiple large squares like this, and we'll say that they're counties in a very nice, orderly country of some sort. And you can train the model at the county level, but predict at the target level, so at the pixel level. Now, this is an ecological fallacy, and some of you all might notice that. But in practice, it kind of works, and we'll talk a bit about why. So going back here, we've got our source area and value. We've got our target areas we want to predict for. We've got our ancillary data that is also at the target resolution. And we train some model, in this case, a linear regression of some sort. Now, this is not complete. It doesn't have all the weights, but this is for an example. And so you then essentially have these target weights. You can then do what we call a relative redistribution. So for each source area, you're actually going to normalize these individual weights at the pixel level by the sum of weights in the source area. So in this case, when we sum up all of these pixels here, we get a value of 0.81. So we divide them all by 0.81. So what this means is that for each source area, so if we look here in the bottom right, we've got 3. We are going to be relatively distributing the population count in area A relative to its weights. In area B, we are going to distribute it relative to its weights as well, independent of A. And same with C. So A, B, and C are all using the same model that's trained on all of the units you have, all the source units, but they are being relatively distributed within their own bounds. And this is what gives you the volume preserving quality, meaning that once we distribute the population count of 100 here in this example to the individual pixels, they will still add back up to 100 later. And that's key, right? So in this case, you can see an example here where once we have the normalized weights, we multiply by 100, and we get our output population at the target areas. So you can see we had some area of land cover that was 200 that had a weight of 0, a normalized weight of 0, and therefore has a population in the final distribution of 0. You have other areas that were 0.1, and I think that corresponds to a common code for built settlement. So that comes from here. It has a normalized weight of 0.12, and then that results in a final population of those pixels of 12.3. Are there any questions on this general procedure of redistributing these values? So, okay, good. If it's fine if there are later, that's fine too. So the main thing is that you are getting these weights and redistributing, and that they can add back up. How you determine those weights, in this case we had a linear regression, doesn't matter. There are pluses and minuses to every possible model that you can use to determine these weights. But that's going to depend upon your application, right? And I'll talk a bit about random forests and why I tend to use them and why, you know, other folks tend to use them in some applications and what some of those limits are, though. There is a caveat, though. Once you have this pixel level population layer, that doesn't mean you can go and be like, oh yeah, there's 12.3 people in that pixel, right? Not really. In practice, the uncertainty that is attached at the pixel level is unknown, and it's unknown mainly because of this relative redistribution. We can get confidence intervals for the weights from this model, but because you are relatively redistributing and multiplying this step, the error and uncertainty does not propagate mathematically through to the pixel level. So the uncertainty is completely lost, and we have no idea what the uncertainty or error is on that. There are some rules of thumb that you can go by. If the source area is very spatially different in its resolution from the target area. So for instance, let's say our source area has a square, and it's a 10 kilometer by 10 kilometer square. And our target unit is a 100 meter by 100 meter square. You are going to have greater uncertainty introduced because of the spatial difference in those units than if you were to have a 1 kilometer by 1 kilometer square and trying to disaggregate to 100 meter by 100 meter. So that difference in spatial resolution between source area and target area is introducing uncertainty into your final output. It's also introducing uncertainty into the model in this case. If you are training the model at the source area level and you are assuming that the relationships seen there are the same at the pixel level, that is introducing a whole lot more uncertainty, right? Because we can have differences in observed relationships across spatial scale. The bigger the difference in spatial scale, the greater possibility or likelihood that you're going to have different relationships that might be significant. So sometimes you can get odd things. Another issue is when you are training this model here on the right, a linear regression in this case, your Y value is not the population count. We are actually predicting population density that we are then using as target weights. So that means that A is not, its observed value is not 100 in this model. It is 100 divided by the area of A. And in fact, we log transform it in practice as well because we get some better results and then back transform it when we predict. But the main thing is that you are actually, with this model, you're predicting the average population density over the unit. So when we are relatively redistributing, you can it's giving you the count, but we are not actually predicting population counts originally with this in our weights. So if you have a larger unit, you are, because of the modifiable areal unit problem as described in OpenShaw 1984, you're going to lose variance and information because you are generalizing over a larger area. So these are some caveats to keep in mind when you're using these outputs, right? And in fact, it's why in best practices, when you get this pixel level, that's great, right? It could be 10 meters resolution, it could be 100 meters resolution. The quote, the unanswered question is how fine is fine enough? And the general vague answer is, well, it depends on your application, because the benefit of having a pixel level resolution of a certain value is, can it be aggregated up to some intermediate unit that's not the source area, but is useful for your application? And the more you aggregate this up to a resolution that's closer to your source area, you're kind of also taking advantage of the modifiable area unit problem in aggregating some of the uncertainties and hoping that the pluses and minuses kind of cancel out a bit. That's assuming that the errors are normal. And that they will cancel each other out. It's not known as to whether it is or isn't. But generally, when you aggregate these, you do reduce some of the uncertainty and error, although that error is not homogeneous, so it can't be assumed that all of them are decreasing that equally, and it's very context dependent. So if you want to read more on Dasymetric disaggregation, the two main papers I would recommend is Minnis 2003, so that's Jeremy Minnis, and then Minnis and Holtgren 2006. And then there are others by Dave Martin, who's down at Southampton, who's done some good stuff with it in the 90s and onwards, as well as a few papers by Brewer and Eicher, E-I-C-H-E-R, from the early noughts. And they're quite good to read through. There's also a good one on a possible way of giving some rough bounds of uncertainty for Dasymetric disaggregation by Stefan Leik out of University of Colorado Boulder, that I believe was done with Nagel, N-A-G-L-E, around 2014. So I would recommend those. So what if we are using for our weight determination a random forest? Well, first, how will we do that? And so the first person to really sort of use a random forest for this was Forrest Stevens, a colleague of mine at the University of Louisville, with some other folks, Andrea Gahn, Catherine Leonard, and they utilized a random forest in this. And essentially what they did is they took their census-based population counts, they calculated their average population densities for each subnational area. They have their covariate data that's at the pixel level, and they calculate summaries of those at the subnational area level. So that means, going back up here, their covariates that they're training at, they're taking averages or average distance to each of these classes at the source area level. So you're not only training on the average population density, you're training on some average or aggregate measure of the covariates for each source area as well, also introducing uncertainty. So once you have your covariates and your population densities at the subnational level or source area level, you can train a random forest. So what's a random forest, right? So we'll come back to this process in a second. So a random forest can generally be described by this process diagram, but we're going to break it down a bit more. So going back outside of this, so ignore this figure on the left, and we're going to do some sketching fun. Let me increase the thickness of this line here. So a random forest is what's known as a ensemble method. An ensemble method is a type of method that takes many independent models and brings together all of their predictions in some way. A random forest is an ensemble or a collection of individual classification and regression trees, or carts. So classification and regression trees are essentially these trees that, you can start with one, and we'll describe this as a network, essentially. You start off with your original data in some way. And we'll use cars, the classic cars data set for the examples here. So you start off with this, and you are trying to iteratively divide this data into smaller and smaller, more homogeneous groups, right? To then predict, or whether that's a classification or a regression of some sort. So let's say we're trying to predict for miles per gallon in this case. So the fuel economy of a vehicle. And we've got things in this such as number of doors, color of car, manufacturer, class of vehicle. And so essentially a classification and regression tree will iteratively subdivide based upon some algorithm and information value into successively into two data sets at every split. And it will do this based upon some form of decision. So you might say, okay, we are going to test this along several covariates, whether that's number of doors or color. And eventually for that split, it decides on a rule. And it's like, okay, doors greater than, sorry about that. Let me turn off my phone. For doors greater than 2, we will shift everything into the subset on the right. And for doors less than 2, we will subset everything onto the left. And then it will go down to the next split. And, maybe it has some way of choosing a different covariate. And it does this so on and so forth until you meet some sort of stopping criteria, whether that means there's only one observation in each node, or there is 5 observations, or there's some sort of criteria that tells it to stop. The split is assessed for its suitability based upon an information criteria or entropy, something that's trying to declare how homogeneous the data is, and that's how it will choose between one covariate versus the other. And there's many different types or flavors of classification and regression trees, like C5, other things, and mainly these just have to do with how they decide the splitting and the algorithm for choosing the covariates. So that aside, a random forest is many carts. In fact, usually it's about 500 or so at a minimum. And the main paper for this is by Leo Bryman, I believe it's pronounced, from 2001. And there are many different flavors of random forest since, but we're just going to focus on the basic one here. A random forest is useful for a couple of reasons. There's almost no manual tuning. It's very robust to small and large data sets, as well as outliers and correlation. And it's relatively automatable, and it's parallelizable. So you can run it in parallel very easily, both in terms of predictions and training. And it's for this reason, when I was working on population modeling across various countries, that our group selected this because we had different data sets, different sizes of data sets, different quality of data sets, different relationships, and we didn't want to have to go and manually tune these many times. So that's why we chose to use random forest, but you might use some other thing as well. So the key thing behind a random forest, besides the fact that it's many classification and regression trees, is that it does this thing called bagging, which can be thought of as bootstrap aggregating. So essentially, you have the main data set here on the left, and for each tree that you are making independently, you are going to randomly select with replacement a sample from the full data set. And that size varies a bit, but in general, once you are done bagging across all the trees, each observation is present in about 2/3 of the bagged samples. So typically, you've got about 2/3 of your sample here and 1/3 in your out of bag sample. So we withhold the out of bag sample. We have the bagged sample. We use that bagged sample to train a single tree. We then make the tree by randomly, so this is the random and random forest, it randomly selects a subset of the variables, and this is known as the mtry parameter in a random forest. at least within the R iteration. And it will automatically adjust and fit itself to determine what is an optimal M-try value. So it might be 2 random covariates, it might be 3 random covariates, it might be 10. It depends on the data. What that means is that each of these nodes, when you're going to split, it is going to randomly select 2, 3, however many of those variables, and then in those variables, find an optimal split value. So say we are looking at average time to timing belt change in a vehicle. That's a large continuous one. So we have some sort of continuous line here for miles to timing belt change. And essentially the algorithm is going to iteratively go through and try and find the best splitting point to where it can say, okay, everything to the left is one subset, everything to the right is the other subset. And it compares amongst the variables, meaning that, and selects the one that has the best homogeneity criterion for this. So that means that at each of these nodes, you can be splitting by a different random subset of covariates, and you're not always comparing the same subset of covariates. This means that each of these trees is relatively uncorrelated combined with the unbagging to the other trees. And this is why we don't have to worry so much about intercorrelation between the trees in this model. So this random feature selection and subdivision is repeated until your stop criteria is met. And cool, we've got a tree, right? So we've got one tree. We then bring in that out of bag or withheld data from the bag sampling, and we run it through the tree and estimate the error that's produced by that tree. And we get that out of bag error for that single tree. This is important later. So we'll keep growing trees until we get to the specified number, so minimum of 500 typically. And we stop and we're recording out of bag errors the whole way. And when we meet that stopping criteria, we now have our random forest. Nice thing is we can then take that out of bag error of all the individual trees and bring them together to get the generalized random forest model error. And this is essentially a internal cross-validation. It's not as good as a fully withheld cross-validation that's withheld prior to doing the bagging, but in practice, it's quite close typically to a withheld cross-validation, at least in my experience. So this is another useful aspect of random forests. So we've got this when you run the random forest in a predictive mode, you have all of these trees and they each put out some sort of predicted value and so forth. And then it's all brought together by averaging. So they will all have these different predictions, and our prediction is the average of those predicted values from the trees. A big limit with random forests, though, is that they can only predict inside of the range of values that they are trained upon. So if your lowest value is a population density of 5.5, and your highest is a average population density of 85 per square kilometer, your random forest, any one of those trees cannot predict below 5.5 or above 8.5. Regardless of whether or not those target areas that you have, you might know actually have true values of 0 there, right? Or you can assume that. It can't predict below 5.5. And in fact, it's probably never going to predict 5.5 because, again, you're taking an average of all of the trees, right? So similar on the top end, you may know in an urbanized area at the target level, you're going to have population densities that are higher than 85. But if your highest value at the area level is only 85, you're never going to be able to predict above 85. And again, you're probably not going to predict 85 in any one of those pixels because it's averaging, right? So like most models, a random forest will average the results down towards some sort of mean or median value, right? And this leads to some practical issues when we are predicting for population densities. We have a propensity to underpredict in urbanized areas or high density areas, and overpredict at the pixel level in rural areas. Now, what this means in practice is you might have something like a pixel in a rural area that's something like 0.0004, which seems like, okay, yeah, whatever. That doesn't mean anything. But over a subnational unit, if you have 100 or 1,000 of these or 10,000 of these sorts of values, they can add up to whole people or tens of whole people or even hundreds of people, depending on how big the area is and how many of those units you have, those small overestimations. Similar in urbanized areas, or high density areas, you will have lower population densities. So you're going to have a relative under density estimation in any of those pixels, despite them all adding back up to the original count of 100 or whatever. Same thing in the rural areas. So we have an issue of over dispersion in rural areas with this model, and the issue with under dispersion in the more dense areas. So something to keep in mind with this approach, and this is one of the main limits of using a random forest in this applied setting, but knowing the systemic biases, despite not knowing the overall, the individual pixel level error, is useful for us as practitioners, right? And it's something that you can assess. Now, some of you all are probably thinking, well, we can just round off the values, that are that close to zero and assume they're zero. We've tried that. It tends to actually produce worse values than not when you look at when you assess for error at the pixel level. And again, in an applied setting, you shouldn't be using the pixel level values by themselves, right? You should be reaggregating to some level that is somewhere between your target area and your source area. So hopefully some of those values average out, they add up, and it minimizes some of that over dispersion, under dispersion issue. This is an area where folks are researching how to better improve this, but currently there's no useful way of really doing this especially at scale. So before I overview the practical real quick and turn you all loose, I want to talk about how you might assess error once you've done this. So if you've got a model where you've got, say, admin level 2 units here in red, and you've also have the benefit of having like admin level 3 units here outlined in blue that are nested within the red units. And maybe you even have further units nested within each blue unit that are outlined in green here, which is not colorblind friendly, I realize. I'll outline them in white. There we go. And I won't go through all of these, but you get the point, right? So you've got admins level 3 or 2, 3, and 4. There are a couple of different ways you could approach this, right? If you're wanting to produce the possibly most accurate, I say possible because there are things that can come into play here. The most accurate pixel level redistribution you want to train, which I'll shorthand with T here, you want to train on 4 and disaggregate from level 4, right? The white outlines. The problem is you have no way to assess error. Possibly a problem, right? Because you have no admin levels held in reserve, other than much coarser ones. You could do something that we've called in practice one level up validation, where you train on 4, disaggregate on 4, and validate with 3, right? So you take those pixels that were produced and you aggregate them to level 3 boundaries and assess the error at that level. It doesn't tell you anything about the finer scale, but it tells you about the error at level 3, right? Not the best, but it gives you something. If you are fine with it, you can also train on admin level 3 and disaggregate from admin level 3, holding admin level 4 in reserve. This is best practice because, again, level 4 is finer than level 3, so we are able to retain some of that spatial fineness and information to compare to our model. So you can then go one level below and assess the error at the admin unit level. Again, so this is not at the pixel unit level, because you won't have that unless you say have point level survey data that's even finer that you can then assess at. The other thing you can do, which is a bit different, is you can train on 4. So you're getting the relationship much closer to the target units in the random forest. So that's kind of minimizing the uncertainty there. And then you disaggregate using level 3. So you are prioritizing information in the weight generation and minimizing the spatial disconnect there over having an increased spatial difference between your source units and your target units. And you can then go and assess the error using I'm sorry, I should have done that in white. You can assess the error in using the boundaries for admin level 4. So you're retaining the spatial fineness. Yes, you train the model on admin level 4's relationship with the covariates, but you're actually comparing the boundaries after the fact. The boundaries didn't run into the actual disaggregation procedure because the random forest is aspatial in this. So that's some different ways you can assess error without having a finer scale survey population type data set. So are there any questions on that before I start overviewing the practical a bit?
I have a quick question on
Sure.
limits of your boundaries of your predicted variables. So I'm assuming you're using pixel level, you're predicting pixel level population density as your Y, right?
No, so the weights are, well, yes. So you are predicting population density at the pixel level, but you are not using those. If you were to do that right out, then that would just be a straight ecological fallacy, right? It's kind of only permissible because you are then using the relative distribution of values within a unit to relatively redistribute the population counts. So yes, you are predicting population density at the pixel level, but those, you know, it's just used as a relative weight after that. Does that make sense?
So the range of your density value is going to be between 0 and 1 then? So
after you normalize it, yes, for respective to each source area. So yeah, the weights within each source area, once you normalize them, will be between 0 and 1. And those are independent of the source areas next to them. So if you've got several counties, each county, once you normalize the pixel level population densities, they are now your weights, and they will be between 0 and 1 in this one. They will be between 0 and 1 in this one, and 0 and 1 in this one. So within each source area, they have to add up to 1, but they don't cross over boundaries.
Thank you for your answers.
Yeah, no worries. Any other questions? Cool. We can talk more about that in a minute if there are questions. But I wanted to show you all a bit of the practical setup real quick. So the practical is in a Jupyter notebook for Python or an R notebook in our studio for other folks. And essentially on the GitHub, you will see it is laid out as such. And you can download that. I'll put the link back up in a minute. And unzip it in some location. Did I actually download it? Yes, I did. So when you download it and unzip it, you'll see this here. And essentially for our users, I'll give a quick thing here. Martin can address more on the Python. You can open up the training file, and it will essentially have text and figures that walk you through as well as code blocks. So for those who might not have used a notebook before, essentially you can have all these text-based things that guide you along through a workbook with these then code blocks here that you can run interactively by hitting the little green button, or you can copy and paste the code that's in these blocks into the interactive console at the bottom and run them by hitting enter. The main thing you need to do when you open this is make sure that you've got your packages installed properly. And so the package list that you will need is here for on lines 51. Line 51 to be able to run this stuff. So to install this, you'll need to do install.packages, install the packages. Python has its own thing. Martin's got the setup for that. I'll let him deal with that. Once you've installed the packages, the other main thing you need to do to get this to work is to change this variable we're calling root. And so here I've got it set for the path that the folder was in when I was writing this. Obviously, where I've downloaded it now, it is d/GISRUK_Dasy. So I will need to change this accordingly to that for it to work. Does that make sense to folks? So wherever you unzip it, you're going to want to.
Well, Jeremiah, I'm not sure that is the D volume. Actually, the easiest way would be to just remove the paste root and just go with the relative path of that data.
That's fine if you want to walk them through that. This is a little more explicit, and it kind of saves having to explain relative paths to folks that might not be familiar.
Yeah, even fine. The one is fine.
Yeah, so this D yada 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 is specific to my computer I'm on. Yours will be different. It might be M something something. It might be C something something. It will depend on where you download the folder to.
It's weird on this machine. For those who use the laptop, it's easier. For those who use the university machine, the path is much longer because it's
so
volume.
Yeah. Just do the string starting with data without passing.
But Alessia and Martin will be able to help you all with that. Additionally, so I do have an install packages block here from 124 to 128 that you all can run as well. And then it's just sort of going through the practical where you will make your own weights a couple of different ways, making the model and the output. And if you get done with this, and even if you don't, but later, you can run through the PopRF vignette, which is a vignette that I made that will walk you through how to use the PopRF package. And all the data is open and downloadable to replicate that. And it walks you through a couple of different ways that you can parameterize the model that we didn't cover here. So I will leave it at that and set you all loose. I'll take this back to the GitHub link, and I'll also stop the recording currently as well.